Welcome to an introduction to the foundational database services that are available on AWS. AWS solutions typically fall into one of two categories: unmanaged or managed. Unmanaged services are typically provisioned in discrete portions as specified by users. As the owner of the service, you manage how the service responds to changes in load, errors, and situations where resources become unavailable. If you want to maintain complete control of your database, you can install a relational database management system on an Amazon EC2 instance. This will be very similar to running your database in a physical data center that you own and will be an example of an unmanaged service. Say that you launch a web server on an EC2 instance. Because Amazon EC2 is an unmanaged solution, that web server will not scale to handle increased traffic load or replace unhealthy instances with healthy ones unless you specify that it use a scaling solution. It could be the auto-scaling service that you use. The benefit of using an unmanaged service is that you have a more fine-tuned control over how your solution handles changes in load, errors, and situations where resources become unavailable. There is also some configuration for managed services. For example, you can create an S3 bucket and then set permissions for it. However, managed services typically require less configuration. Now we will look at the challenges of running an unmanaged standalone relational database. Then you will learn how Amazon RDS addresses these challenges. When you run your own relational database, you are responsible for several administrative tasks, such as server maintenance, energy footprint, software installation and patching, and database backups. You're also responsible for ensuring high availability, planning for scalability, data security, and operating system installation and patching. All these tasks take resources from other items on your to-do list and require expertise. To address the challenges of running an unmanaged standalone relational database, AWS provides RDS, a service that sets up, operates, and scales relational databases without any ongoing administration. With Amazon RDS, your primary focus is your data and optimizing your application. With Amazon RDS, you manage your application optimization. AWS manages installing and patching the operating system, installing and patching the database software, automatic backups, and high availability. AWS also scales resources, manages powers and servers, and performs maintenance. Offloading these operations to the managed Amazon RDS service reduces your operational workload and the costs that are associated with your relational database. Let's take a closer look at the details of RDS. The basic building blocks of the Amazon RDS is the database instance. A database instance is an isolated database environment that you can contain multiple user-created databases. You can access your databases using the same tools and applications that you use with a standalone database instance. When setting up your database, you pick an instance class and the type of storage you need for your database. Database instances and storage differ in performance characteristics and price. This enables you to customize your performance and cost to the needs of your business. When you choose to create a database instance, you specify which database engine to run. Amazon RDS supports 6 database engines: MySQL, Amazon Aurora, Microsoft SQL Server, PostgreSQL, MariaDB, and Oracle. There are many different ways to configure your RDS implementation. For example, you can run an instance in an Amazon VPC. When you use a VPC, you have control over your virtual networking environment. You can select your own IP address range, create subnets, and configure routing and access control lists to control access to your database. The basic functionality of Amazon RDS is the same whether or not you run it in a VPC. Usually, the database instance is isolated in a private subnet, and it's only made directly accessible to the applications that you choose. One of the most powerful features of Amazon RDS is the ability to configure your database instance for high availability with a multi-AZ deployment. When you configure a multi-AZ deployment, Amazon RDS automatically generates a standby copy of the database instance in another availability zone within the same VPC. After seeding the database copy, transactions are synchronously replicated to the standby copy. Running a database instance in a multi-AZ deployment can enhance availability during planned system maintenance, and it can help protect your database instance if there is ever a disruption within the availability zone. If the main database instance fails in a multi-AC deployment, Amazon RDS automatically brings the standby database instance online as the new main instance. The synchronous replication minimizes the potential for data loss. Because your application references the database by name by using the DNS domain endpoint, you don't need to change anything in your application code to use the standby copy for failover. Amazon RDS also supports the creation of read replicas for MySQL, MariaDB, PostgreSQL, and Amazon Aurora. Updates that are made to the source database instance are asynchronously copied to the read replica instance. You can reduce the load on your source database instance by routing read queries from your applications to the read replica. This is a configuration that you will choose if you have an application with a high number of read operations. Amazon RDS is a great solution for many types of database scenarios, but some of the more common use cases include web and mobile applications that need a database with a high throughput, massive storage scalability, and high availability. Here are some common requirements that could indicate that RDS is the right solution for you. Do you need to support complex transactions or complex queries? Do you have a medium to high query or write rate, up to 30,000 input outputs per second? You don't need more than a single worker, node, or shard. Some of the requirements that might mean RDS is not the best solution for you include: you need massive read writes, for example, 150,000 writes per second. You have really large data sets or throughput demands. Or you have very simple get or put requests and queries that might be better suited for a NoSQL database. If Amazon RDS is not a good candidate for your requirements, you should consider one of the other database services such as Amazon Aurora or Amazon DynamoDB, which we will review in other videos in this series. When you begin to estimate the cost of Amazon RDS, consider the clock hours of service time. You are billed based on the amount of time your service is running. The physical capacity of the database you choose will also affect how you are charged. Database engine, instance size, and memory class will impact the cost running your database RDS instance. Database purchase type also has an impact on your cost. When you use on-demand instances, you pay for compute capacity for each hour that your database instance runs. There is no minimum requirements or commitments. You can also select reserve instances. With reserve instances, you make a one-time upfront payment for each database instance that you want to reserve for a 1-year or a 3-year term. The number of instances you create will also impact your cost. For example, you might want to provision multiple database instances to handle peak loads. Selecting the best storage configuration is another factor that will impact the cost of running your RDS implementation. There is no additional charge for backup storage of up to 100% of your provisioned database storage for an active database instance. After the database instance is terminated, backup storage is billed per gigabyte per month. Finally, consider the number of input-output requests that will be made to the database, as well as any data transfers. Inbound data transfer is free, and outbound data transfer costs are tiered. Depending on the needs of your application, you might be able to optimize your costs by purchasing reserved instances. Thanks for watching. We'll see you in the next video. Hello, and welcome to this Academy Cloud Foundations demonstration. In this segment, we're going to be speaking about Amazon Relational Database Service, or Amazon RDS. Amazon RDS makes it easy to set up, operate, and scale a relational database in the cloud. It provides cost-efficient and resizable capacity while automating time-consuming administration tasks such as hardware provisioning, database setup, patching, and backups. It frees you to focus on your applications so you can give them the fast performance, high availability, security, and compatibility that they need. Amazon RDS is available on several database instance types, optimized for memory, performance, or input and output. It also provides you with 6 familiar database engines to choose from, including Amazon Aurora, PostgreSQL, MySQL, MariaDB, Oracle, and Microsoft SQL Server. You can use the AWS Database Migration Service to easily migrate or replicate your existing databases to Amazon RDS. In this demonstration, we go through the steps of creating a MySQL database using Amazon Relational Database Service and the AWS Management Console. We then connected the database in AWS using a MySQL client running on an Amazon Linux EC2 instance. So we are at the console, and we're going to be navigating to the RDS landing page. Once we are on the Amazon RDS landing page, we focus our attention on the orange button that says Create Database. We also notice how the left navigation panel has a number of items related to snapshots, automated backups, query editor, and others. These items are a little bit more advanced, and we suggest that you explore them individually to become familiar with what is it that they do, what benefit they render to you. We're going to click on Create Database. And on the following panel, we get to select the engine that we're going to be using. In our case, the MySQL engine. We get to see Amazon Aurora, MariaDB, Postgres, Oracle, Microsoft SQL Server. In this case, we use MySQL as it is a common database implementation for LAMP stacks. On the MySQL configuration, we're going to click on Next. And RDS gives us a way to be able to choose what type of use case are we going to be applying in this particular case. In our case, we're going to be generating a development and testing database. And we're going to make it applicable for the free usage tier. We're going to click on Next after that. And we get to answer some questions related to this particular database instance. Scrolling down a little bit, on the DB instance class, we're going to scroll up and select T2 Micro. That's going to give us a database engine that's actually applicable for the free tier usage. Because this is a development database, we're not going to be doing multi-availability zone deployment. We're going to leave the storage exactly as is, and we're going to be disabling the storage auto-scaling. Notice how the panel for estimated monthly cost gives you an estimate of what you will expect to pay for this particular implementation on a monthly basis. On the database instance identifier, we're going to give it a name. For master username, we're going to be selecting admin. We're going to be providing the master password and confirm it and click on Next. Following that, a number of advanced settings come into play. As far as the virtual private cloud that we're going to be using to land this particular RDS instance, we're going to select Lab VPC. The subnet group, we're going to keep the same. And for public accessibility, we already have it checked. We don't want it to be publicly accessible. We have no preference for availability zone. However, on the VPC security groups, we have pre-provisioned an RDS security group, which is actually open for the MySQL port 3306. The database name and the port 3306, everything looks good. We're not going to be using identity and access management authentication, so that radio button is selected correctly. We're not going to be using encryption. And for backup, we're going to select 0 days. We're not going to copy any tags. And we have disabled enhanced monitoring. As far as log exports, we're going to leave everything as is. And we're going to be disabling AutoMiner version upgrades. We're also going to be deselecting enable deletion protection. That's all it takes. We're going to select Create Database, and that will immediately begin defining our database instance. We select DB instance details, and we get to observe the database provisioning. Initially, notice on the DB instance status, it indicates creating. We also get to observe how there are a number of CloudWatch metrics already prefabricated as far as being able to observe CPU utilization, DB connections, free storage space, memory, write input outputs per second, read input outputs per second. On the Connect panel, under the endpoint, is where we will receive, once the database is available, the actual host name that we will be using to connect. At this point, we scroll back up, and we're going to be using the refresh button as a way of having the page refresh while we wait for the DB instance status to indicate available. Okay, we now get to observe on the info
that the database instance, myACFDB, is marked as available. So we're ready to go and begin connectivity. As we scroll down on the endpoint and port, we're able to then copy and paste the hostname for connectivity to this database instance. We're going to be maintaining a copy of that RDS endpoint here on a text editor. Following this, we're going to be using the MySQL call to be able to invoke the command line interface to the MySQL database. Providing the password then allows us to begin to interact through the MySQL command line interface. We're going to be invoking some table creation as well as some data population of that table. So a total of 5 statements. The first one, create table, defines the schema, and then of course we populate with 4 names, last names, and phone numbers. All of the queries and all of the requests to the instance actually appear to be working correctly. Now let's do a small query to verify. Pasting a small query will give us the proper result. In this case, we're searching for Chris. We get first name, last name, and phone as a table. So we have successfully provisioned a MySQL database instance using the simplest configuration possible, including the database engine that qualifies for the free tier, using an EC2 instance running the Linux operating environment. We connected to that MySQL database, created a table, populated that table with data, and finally made a small query to verify. This concludes this demonstration for Amazon RDS. Thanks for watching.
This video covers Amazon Redshift. Amazon Redshift is a fast, fully managed data warehouse that makes it simple and cost-effective to analyze all your data by using standard SQL and your existing business intelligence tools. In this video, we will review a slightly more detailed exploration of key Amazon Redshift features and some common use cases. Analytics is an important part of businesses today, but building a data warehouse is complex and expensive. Data warehouses can take months and financial resources to set up. Amazon Redshift is a fast and powerfully fully managed data warehouse that is simple and cost-effective to set up, use, and to scale. It enables you to run complex analytics queries against petabytes of structured data by using sophisticated query optimization, columnar storage and high-performance local disk, and massively parallel queries. Most results come back in seconds. An Amazon Redshift implementation consists of a cluster of leader and compute nodes. The leader node manages communications with client programs and all communication with the compute nodes. It parses and develops plans to perform the series of steps needed to obtain results from complex queries. The leader node compiles code for individual elements of the plan and assigns the code to individual computer nodes. The compute nodes run the compiled code and send intermediate results back to the leader node for final aggregation. Like other AWS services, you only pay for what you use with Amazon Redshift. You can automate most of the common administrative tasks to manage, monitor, and scale your Amazon Redshift cluster. This enables you to focus on your data and your business. Scalability is intrinsic in Amazon Redshift. Your cluster can be scaled up and down as your needs change with a few clicks in the console. Security is the highest priority of AWS. With Amazon Redshift, security is built in, and it is designed to provide strong encryption of your data both at rest and in transit. Amazon Redshift is compatible with the tools that you already know and use. Amazon Redshift supports standard SQL. It also provides high-performance Java database connectivity and Open Database connectivity connectors. This means that you can connect to your Redshift cluster with SQL clients and business intelligence tools of your choice. You can also interact directly with your Amazon Redshift cluster via the AWS console or the AWS command line interface. Next, we'll review some common Amazon Redshift use cases. Increased agility is a common reason for many customers who migrate their traditional enterprise data warehouses to Amazon Redshift. You can start at whatever scale you want and experiment with your data without needing to rely on complicated processes with your IT departments to purchase and deploy software. Big data customers have one thing in common: massive amounts of data that stretch their existing systems to a breaking point. Smaller customers might not have the resources to procure the hardware and expertise that is needed to run these systems. With Amazon Redshift, smaller customers can quickly set up and use a data warehouse at a comparatively low price point. As a managed service, Amazon Redshift handles many of the deployment and ongoing maintenance tasks that often require a database administrator. This enables you to focus on querying and analyzing your data. Software as a service customers can take advantage of the scalability, easy-to-manage features that Amazon Redshift provides. Some customers use Amazon Redshift to provide analytic capabilities to their application. Some users deploy a cluster per customer and use tagging to simplify and manage their service level agreements and billing. Thanks for watching. We'll see you in the next video.
Hello and welcome. This video covers Amazon Aurora. Amazon Aurora is a MySQL and PostgreSQL compatible relational database that is built for the cloud. It combines the performance and availability of high-end commercial databases with the simplicity and cost-effectiveness of open-source databases. Using Amazon Aurora can reduce your database costs while improving the reliability and availability of the database instance. As a fully managed service, Aurora is designed to automate time-consuming tasks like provisioning, patching, backup, recovery, failure detection, and repair. Amazon Aurora is highly available by design. You don't have to do anything to configure high availability. It's built into the Aurora architecture. Aurora is built on a fast distributed storage subsystem, which makes it an ideal solution for large relational database sets. Amazon Aurora is straightforward to set up and supports standard structured query language. It is designed to have drop-in compatibility with MySQL and PostgreSQL database engines so that you can use most of your existing database tools with little to no change. Amazon Aurora is a pay-as-you-go service, which means that you only pay for the services and features that you use. It's a managed service and works seamlessly with AWS Database Migration Service and the AWS Schema Conversion tool. These tools simplify the process of moving your data set into Amazon Aurora from your legacy relational database management system. There are several reasons why you may want to choose Amazon Aurora over other options. One of the primary reasons is the high availability and resilient design that Amazon Aurora offers. Amazon Aurora achieves high availability by storing multiple copies of your data across different availability zones. The data is continuously backed up to Amazon S3. You can use up to 15 read replicas with Amazon Aurora to greatly improve performance of high read use cases. This also reduces the possibility of losing your data. Amazon Aurora is designed for instant crash recovery if your primary database becomes unhealthy. After a database crash, Amazon Aurora does not need to replay the redo log from the last database checkpoint. Instead, it performs this on every read operation. This reduces the restart time after a database crash to less than 60 seconds in most cases. The Aurora architecture removes the buffer cache from the database process. That's why the buffer is available immediately after a restart. This means you do not need to throttle access after a crash while you wait for the cache to repopulate. Thanks for watching. We'll see you in the next video. It's now time to review the module and wrap up with a discussion of a practice certification exam question. In summary, you learn how to describe the difference between a SQL and NoSQL database, explain and describe the functionality for Amazon RDS, Amazon DynamoDB, Amazon Redshift, and Amazon Aurora. You also learn how to perform tasks in an RDS database, such as launching, configuring, and interacting. We also learn how to recognize common use cases for each of the 4 database services we covered. Great work! Let's look at a sample certification question. Which of the following is a fully managed NoSQL database service? In this example, the keyword to recognize is NoSQL. Based on the keyword we identified, the correct answer is B, Amazon DynamoDB. RDS, Aurora, Redshift, and DynamoDB are all managed services, but DynamoDB is the only one that is a NoSQL database service. Thanks for watching.
Welcome to Module 9, Cloud Architecture. This module will address the following topics: AWS Well-Architected Framework, Reliability and High Availability, and AWS Trusted Advisor. Let's get started. Welcome to Module 9, the AWS Well-Architected Framework. Architecture is the art and science of designing and building large structures. Large systems require architects to manage their size and complexity. What do cloud architects do? Cloud architects engage with decision makers to identify the business goal and the capabilities that need improvement. They ensure alignment between technology deliverables of a solution and the business goals. They work with delivery teams that are implementing the solution to ensure that the technology features are appropriate. The AWS Well-Architected Framework is a guide that is designed to help you build the most secure, high-performing, resilient, and efficient infrastructure possible for your cloud applications and workloads. It provides a set of foundational questions and the best practices that can help you evaluate and implement your cloud architectures. AWS developed the Well-Architected Framework after reviewing thousands of customer architectures on AWS. The AWS Well-Architected Framework is organized into 5 pillars: operational excellence, security, reliability, performance efficiency, and cost optimization. Each pillar includes a set of design principles and best practices. In each best practice area, there are a set of foundational questions. Some context and a list of best practices are provided for each question. Thanks for watching. See you in the next video. Welcome. This video will cover the Operational Excellence pillar. The Operational Excellence pillar focuses on the ability to run and monitor systems to deliver business value and to continually improve operations. Key topics include managing and automating changes, responding to events, and defining standards to successfully manage daily operations. There are 6 design principles for operational excellence in the cloud. First, you have perform operations as code. This is where you define your entire workload, that is, applications and infrastructure, as code. By performing operations as code, you limit human error and enable consistent responses to events. Next, we have annotate documentation. Here you focus on automating the creation of annotated documentation after every build. Annotations can be used as input to your operations as code. Next, we have make frequent, small, reversible changes. You should design workloads to enable components to be updated regularly. Make changes in small increments that can be reversed if they fail. Next, you have refine operations procedures frequently. Here you look for opportunities to improve operations procedures and update them as they evolve. Next is anticipate failure. This is where you identify potential sources of failure so that they can be removed or mitigated. Test failure scenarios and validate your understanding of their impact regularly. Finally, we have learned from all operational events and failures. This is where you share what is learned across teams and throughout the entire organization. The foundational questions for operational excellence fall under 3 best practice areas: prepare, operate, and evolve. Operations teams create and use procedures to respond to operational events and validate the effectiveness of these procedures to support business needs. Operations teams collect metrics that are used to measure the achievement of desired business outcomes, business priorities, and customer needs.